Hello everyone, I am Dr. VRAO-PHYSICAL, Assistant Professor, Sri Vayan College, Narsapur. In the last video, we had gone through the HSAB theory and its applications. In fact, it is just a classification of Lewis acids and bases into hard and soft acids and bases to explain the stability of the complexes. Today, I am here with a new concept that is strength of acids. Strength of acids. Strength of acids. At first, we shall go through the Bronsted acids, then after Lewis acids. In general, the strength of Bronsted acid is measured by its acidity constant, and similarly the strength of Bronsted base is measured by its basicity constant. And you are all know that Bronsted acids are hydroacids, and those acids can be represented as HA, where A is a non-metal that we can take chlorine, fluorine, bromine, carbon, sulfur, whatever the non-metal. So those are hydroacids. Now let us go through the strength of Bronsted acids. Already I told you the strength of Bronsted acid is measured by its acidity constant. Now let us take HF as an example, right, from which we shall understand the strength of acids. Okay, so HF, when we dissolve the hydrogen fluoride in water, or HF aqueous dissolved in water, okay, H2O, that is liquid, it dissociates into H3O plus ion plus F minus ion. These are aqueous and F minus is aqueous, that is those ions are present in the aqueous form. And and for this reaction and in this reaction there exists a equilibrium between the products and reactant, and the acidity constant for this reaction can be written as Ka. So where A is the acidity constant, Ka can be written as concentration of H3O plus into concentration of F minus by concentration of HF. Okay, so acidity constant is nothing but is a ratio of concentration of products by concentration of reactant, right? So if Ka comes out to be less than 1, if Ka comes out to be less than 1, okay, when that Ka comes out to be less than 1, when denominator value is more, then Ka comes out to be less than 1. So when Ka comes out to be less than 1, it means that concentration of HF is large than concentration of F minus. That means in simple manner we can say that there is a small fraction of molecules dissociate into H3O plus and F minus. So when Ka comes out to be less than 1, that means concentration of HF is more than concentration of F minus, and that means that concludes that that says that there is a small fraction of molecules dissociate into H3O plus and F minus. That means only small fraction of molecules dissociate into H3O plus and F minus. That means retention of proton by acid favors. So, retention of proton by acid favors. Let us see the next case. If Ka comes out to be equal to 1, if Ka comes out to be equal to 1, that means concentration of HF is equal to concentration of F minus. That means that says that complete dissociation of molecules, complete dissociation of molecules. So, that means acid strength depends on dissociation of its molecules in water or in solvent. So, acid strength depends on dissociation of acid in solvent. So, higher the value of Ka, higher the value of Ka, higher the value of Ka, stronger is the acid. Similarly, lower the value of Ka, lower the value of Ka, weaker is the acid. Higher the value of Ka, stronger is the acid. Stronger acid. Lower the value of Ka, weaker acid or weak acid. So, we can conclude that acid with the highest Ka value is the strongest acid, and acid with the lowest Ka value is the weakest acid. Okay. So, you should keep in your mind that acid with the highest Ka value is the strongest acid, and the acid with the lowest Ka value is the weakest acid. Similarly, it holds good for Bronsted bases also. Right. Now, let us go through the factors affecting the acid strength, factors affecting acid strength. Okay. Factors affecting acid strength. Factors affecting acid strength. Already I told you acid strength depends on its dissociation in solvent or in aqueous medium. Okay, I repeat, acid strength depends on its dissociation in solvent or in aqueous medium, right. So, the extent of Bronsted acid, the extent of dissociation of Bronsted acid depends on strength and polarity of HA bond. I repeat, extent of dissociation of Bronsted acid, extent of dissociation of Bronsted acid depends on strength and polarity of HA bond. Okay, already I told you Bronsted acid is being represented by HA, where A is a non-metal. So, strength of HA bond, okay, strength of acid, strength of Bronsted acid. Already I told you extent of dissociation of bond between the hydrogen and atom A depends on strength of this bond and polarity of this bond. Polarity of this bond. I repeat, strength of this acid or dissociation of acid, dissociation of acid depends on strength of this bond and polarity of this bond. For example, case 1, when strength of the bond decreases, when the strength of the bond decreases, that means strength of the bond, that means the strength of the bond, that means the bond between H and A. When the strength of the bond decreases, then the energy required to break the bond decreases. That means that can give easily, that can give the proton easily. That means that is a stronger acid. So, when strength of the bond decreases, that means the energy required to break the bond decreases, and that makes the acid strong. Right. Next, second case. When the polarity of the HA bond increases, when the polarity of HA bond increases, when the polarity of HA bond increases, that means the electronegativity difference between the atoms H and A increases. That makes the marked charge separation between these atoms, and that marked charge separation favors the cleavage of HA bond, and that makes the acid strong. Right? So, when this HA bond and the polarity of HA bond increases, that means electronegativity difference between the atoms H and A is considerable. That makes cleavage of bond easier, and that makes the acid strong. Okay, you can understand this by with the examples. Okay, so example 1. When we comparing the elements of same group, in the periodic table, then strength of the bond decides, then the strength of the bond is a major factor in deciding the acid strength than the polarity. That means, for example, if you take HF, HCl, HBr, HI, these are the elements of same group. When we comparing the elements of same group in the periodic table, then the strength of HA bond, and the strength of HCl bond, and strength of HCl bond, and strength of HBr bond, and strength of HA bond. When we comparing the elements of same group in the periodic table, strength of HA bond decides the acid strength than the polarity. For example, from fluorine to iodine, size increases. And from fluorine to iodine, size increases. So, size increases. When size increases, the bond between the atoms, the strength of the bond between the atoms decreases. The strength of the bond between the atoms decreases. So, from fluorine to iodine, size increases. That means bond strength decreases. That means from HF can take the higher energy to break, but whereas HI that take lowest energy to break. That's why HF can leave the proton easily. So, HF is the strong acid. And you keep this point when we comparing the elements of same group. This is holds good when we comparing the elements of same group. So, highest acid is HCl, HBr, HI. So, strongest acid is HI. Right? Next, when we comparing, so acid strength increases, size increases, acid strength increases. Example 1. And example 2, when we comparing the elements of same period, when we comparing the elements of same period, and that means when we are comparing the hydro acids of elements of same period, then polarity of the bond decides the acidic strength than strength of the bond. Let us go through the example. Okay, I repeat, when we comparing the elements of same period, then the polarity of the bond decides the acid strength. Okay, for example, nitrogen, for example, if we take a carbon family, nitrogen, oxygen and fluorine, these are the elements of same period. And you can take the acids CH4, NH3, H2O, HF. These are the Bronsted acids, right? So when we comparing, here we are comparing the elements of same period. So what is that rule? When we comparing the elements of same period, polarity decides the polarity of the bond between the atoms decides the acidic strength. But from carbon to fluorine, electronegativity increases. So that's why the bond between the atoms and the element with the highest electronegativity can make the highest polarity. So from carbon to fluorine, electronegativity increases, so polarity of the bond also increases. That's why, so strength of the acid in this case, HF being the strongest acid and CH4 is the weakest acid. This holds good only in the case of when we are comparing the elements of same period. And for example, and another example, example 3, when we comparing the elements of different period and different group, when we comparing the elements of different group and different period, then the strength of the bond decides the acidic strength. Okay, I repeat, when we comparing the elements of different groups and different periods, then the strength of the HA bond decides the acidic strength. For example, HI, H2S and CH4, these are the elements of different groups and different periods. In this case, the HA bond, the HA bond means I generalize this concept HA bond, that is the bond between H and I. So the bond between this H and S, and the bond between the carbon and H. So the bond here, the HA bond strength is more. HA bond strength is more because HA bond strength is weak, because I has a large size, so it has a large size atom, that's why its bond strength decreases, so it can easily give the proton. So HA is the strongest acid than H2S, and H2S is the strongest acid than CH4. Right? So when we comparing the elements of same group, strength of the bond decides the acidic strength. When we comparing the elements of same period, polarity of the bond decides acidic strength. When we comparing the elements of different groups and different periods, strength of the bond decides the acidic strength. Right? Okay. And now let us go through the oxo acids. What happens in the in case of oxo acids? Oxo acids. When we comparing the acidic strength of oxo acids of the same group, for example, HFO HClO, HBRO, HIO, okay, HFO, HClO, HBRO, HIO. In this case, with increasing the electronegativity, and when we comparing the acidic strength of oxo acids of the same group, then we should consider the central atom with the highest electronegativity can central atom with highest electronegativity can make the acid strong. So, HF, here the fluorine has highest electronegativity among the chlorine, among these chlorine, bromine, iodine. So, HFO is the strongest acid than HClO. HClO is the strongest than HBRO. HBr is strongest than HIO. So, when we comparing the oxo acids of the same group, then you should consider the electronegativity of central atom. The oxo acid in which the central atom has highest electronegativity is the strongest oxo acid. And if we can extend this HFO to HCl. I am very sorry. Actually, this HF does not form the oxo acids. Actually, we can find the oxo acids for chlorine, bromine, iodine. We can find the oxo acids for chlorine, bromine, iodine only. So, here the chlorine has highest electronegativity than bromine, and bromine has highest electronegativity than iodine. So, HClO is the strongest acid and HBRO is the strongest acid than HIO. Okay, and we can extend this HClO2 is greater than HBrO2 than HiO2, and HClO3 is greater than HBrO3 greater than HiO3, and HClO4 is greater than HBrO4 is greater than HiO4. So, only thing that you should keep in your mind that when we comparing the oxo acids of same group, then you should consider the oxo acid in which the central atom has highest electronegativity is the strongest oxo acid. But what happens when we comparing the oxo acids of same element? Okay, for example, if you take the oxo acids of chlorine, that is HClO4, so that is HClO4, HClO3, HClO2 and HClO. What happens when we are comparing the HClO4, HClO3, HClO2 and HClO? Okay, in this case, you should calculate the oxidation state of central atom, and the oxo acid in which the central atom has highest oxidation state is the strongest acid. For example, if you take the HClO4, you can calculate the oxidation state 1 plus x minus 8 is equal to 0, that is x minus 7 is equal to 0 and x equal to plus 7. Here the oxidation state is plus 7, and here the oxidation state is plus 5, and here the oxidation state is plus 3, and here the oxidation state is plus 1. So, in this case, the high oxo acid in which the central atom has the highest oxidation state is the strongest oxy acid, right? So, but when we comparing the oxy acids of same group, you should consider the electronegativity of central atom. The oxo acid in which the central atom has highest electronegativity is the strongest oxo acid. But when we are comparing the oxo acids of same element, you should calculate the oxidation state of the central atom. So, the oxo acid in which the central atom has the highest oxidation state is the strongest acid. But one thing is in general the strength of with increasing the oxidation state of the central atom in the oxo acids, acid strength increases both in metals and non-metals except in oxo acids of phosphorus. Okay, this is the only exception that we can find in the oxy acids. Okay, so for example, if you take the oxy acids of phosphorus, H3PO2, H3PO3, H3PO4. So, these are the oxy acids of phosphorus. What we know when we comparing the acidic strength of oxy acids, so the oxy acid in which the central atom has highest oxidation state has the is the strongest acid. But there is a exception for oxy acids of phosphorus. Here the oxidation, let us calculate the oxidation state in the phosphorus H3PO2, H3PO3 and H3PO4. H3PO4 3 plus x minus 4 is equal to 0, that is plus 1, that is plus 1. And here we can get 3 plus x minus 6 is equal to 0, that is x equal to plus 3. And here 3 plus x minus 8 is equal to, and x minus 5 is equal to 0 and x equal to plus 5. So, plus 5. What we know? We know that oxy acid with highest oxy acid in which central atom has highest oxidation state is the strongest oxy acid. So, basing on that statement, strongest acid is H3PO4. But oxy acids of phosphorus, when we compare, when we concerns with oxy acids of phosphorus, H3PO2 is the strongest oxy acid of phosphorus. How it is possible? How it is possible? Because if you take this, if we write this structure P double bond O and OH, if you write this structure P double bond O, and we can understand this reason behind this by going through the structures of oxy acids of phosphorus. Okay. We can find the three groups, that is PO group, PH group and POH group. 1, 2, 3. Let us go through why this H3PO2 is actually H3PO2 in the central atom oxidation state is plus 1, but though the center oxidation state of central atom is plus 1, it is strongest acid. Because why? Because if you the reason can we can get the reason from the structures. For example, in this H3PO2, there is the three types of bond groups, that is PO group and PH group and POH group. And you can find this if you observe this structures of oxy acids of phosphorus, you can find that there is one PO group and there is one POH group. And there is a one PO group and there is two OH groups and POH groups, that is 1:2. And there is only one PO bond and there is three POH groups, that is P 1:3. 1:3. Of course, in this three groups, PH group, PH bond is non-polar, because electronegativity of phosphorus and electronegativity of hydrogen are almost same. So, pH bond is non-polar, but a PO bond is polar because the electronegativity difference between phosphorus and oxygen. Marked electronegativity difference between phosphorus and oxygen. So, actually the electronegativity PO group, actually the PO group induces the polarity in POH group. So, that polarity, owing to that induced polarity, this H3PO2 can lose the proton easily. But what happens here is also we can find the OH group. So, here the P double bond O group, the number of P double bond O groups, PO groups per POH group increases from left to right. So, 1 PO bond, 1 POH bond, 1 PO bond, 2 POH bonds, 1 PO bond, 3 POH bonds. Actually, this PO group induces polarity in POH group. That's why it can easily lose the proton. But what happens in this case? Why this acid is weak acid than this? Because here the number of POH groups per PO group increases. So, this PO group ability decreases in inducing the polarity, because for one PO bond there are 2 POH bonds. So, it is incapable in inducing the polarity in these 2 groups. But here is only one PO group that can induce polarity in one POH group, but here the number of POH groups increases. So, its ability decreases in inducing the polarity. So, for H3PO4 there are 3 POH groups for one PO group. So, acidic strength, so it is easier to induce the polarity in POH group for PO group, provided there is 1:1 relationship, that is there is one PO group for one POH group. So, this is the this is the only one and only exception in the oxy acids of in the oxy acids. Okay, if you compare the oxy acids of any element, in that you can find the oxy acid in which central atom has highest oxidation state is the strongest oxy acid. But when we are comparing the oxy acids of phosphorus, you can find the strongest oxy acid of phosphorus with the least oxidation state of central atom, right? So, these are the Bronsted acid strength, and these are the factors which decides the Bronsted acid strength. Okay, now let us go through the Lewis acid strength. Lewis acid strength. Lewis acids. Already we know that Lewis acids are all simple cations are Lewis acids, and the compounds in which central atom has incomplete octet is a Lewis acid, and the compound in which central atom has vacant orbitals is a Lewis acid, and the compound with the multiple covalent bonds is the Lewis acid. So, what are the factors that decides the Lewis acidic strength? There are 4 factors are there to decide the Lewis acidic strength. Okay. So, with increasing the electronegativity atoms, with increasing the electronegative atoms attached to the central atom, Lewis acidic strength increases. We can understand this with example. For example, if you take SO3 and SO2, those two are Lewis acids. Which is strongest Lewis acid? Already I told you that Lewis acid in which number of electronegative atoms attached to the central atom increases, Lewis acidic strength increases. So, here the number of electronegative atoms are 3 oxygen atoms are attached to the sulfur, and here the only 2 oxygen atoms are attached to the sulfur atom. So, the Lewis acid in which more electronegative atoms are attached to the central atom is the strongest Lewis acid. And second one is with increasing the charge on the ion, makes it a relatively strong acid. For example, you can understand this with example. That is, for example, if you take Sn stands plus 4 and Sn plus 2, Fe plus 3 and Fe plus 2. The ion with the highest charge on the ion, is the strongest Lewis acid. Okay, so and the third one is if the charge on the ions is same, for example, lithium plus Na plus and K plus, what happens in this case? And the ions on the charge on the ions is same, then the decreasing in the ionic radii increases the Lewis acidic strength. Of course, here the charge is same, but in lithium plus there is decrease in ionic radii. And when comparing the ionic radii of Li plus when comparing the ionic radius of lithium and sodium, lithium has lowest ionic radii. So, lowest ionic radii, the Lewis acid with lowest ionic radii or the cation with lowest ionic radii is the strongest Lewis acid. And one more factor is with increasing the nuclear charge. Lewis acidic strength increases. For example, if you take Li plus beryllium plus 2 and boron plus 3, here the nuclear charge increases. The nuclear charge increases. The highest nuclear charge is the strongest Lewis acid. So, boron plus 3 is the strongest Lewis acid. So, these are the examples for Lewis acidic strength. These are the factors which can influence the Lewis acidic strength. Okay, I hope you all understand this concept. Thank you.